Hello, Mr. Avery, are you alright?
Yeah.
Yeah, we have talked about the games in these few days. We talk about the two-player zero-sum game. Yeah, two-player zero-sum. One takes, I make a move, you make a move. Yeah, I know exactly what happened on the game, and you know the same exactly. Let's call two-player zero-sum game. I play to win. Yeah, I win, you lose. Yeah, I lose, you win. Yeah, that's zero-sum. Okay. It's a Pokemon card, zero-sum game, two-player. Pokemon. That's poke. Yeah. That Pokemon. Do you know play poker cards? Is that a two-player zero-sum game?
I'm not sure.
You're not sure. I mean, for the Pokemon cards, is it a two-player? No. It could be many player, multiplayer. But the thing is that the player does not know.
I know two-player, not really.
Yeah. So I play the poke cards. I don't know what happened on your hand. Yeah. So this is not a two-player zero-sum game. Okay? Because each player is, all the players do not share the same kind of information, right? Yeah. You don't know what's in my hand, right? That's not two-player zero-sum game. We talk about the min-max. Min-max is a kind of search algorithm in the game tree, right? So we have a max, we have a tree, yeah, we have a tree. Game, the node will be, each node will be the state of the game, yeah, each state. So one player is trying to maximizing it, the other one is trying to minimizing it. Okay, so it takes turn, right? It takes turn. So for example, this one is trying to maximize, this one is trying to minimize, and this one is trying to maximize, minimize then. Okay, so min-max. Yeah. And we also talk about the simplified implementation of min-max, which is called NegaMax. Yeah, NegaMax. The problem of the min-max is what? Is that in its implementation, we have to write the same bit of code twice, right? So if maximizing, we are trying to find the max value among each kit. And if it's minimizing, yeah, we're trying to find the minimum value of the kit. And these two bits of codes are similar, it's just different directions, right? So with the NegaMax, we're simplifying both scenarios. We combine both scenarios in one function without the if statement, if check. So so you just both cases will be trying to maximize the value. How does that work? Why is that? Because look, if we want to get the maximum of A and B, what does it equal? If we put a sign for minus A minus B, if we get the mean, and then it will be equal to the mean, we put a sign, negative sign. Yeah? Alright? Is it alright? Let's say 10, 20. So let's put a sign over minus 10, minus 20. So what's the minimum of it?
Minus 20.
Minus 20 is the minimum. So minus 20, put the two sign, cancel out, that'll be 20. That's the thing we're looking for. Right? Yeah? This equation. How do we prove that? If we saying A is bigger than equal than B, right? Max A B will be A, right? Yeah? If we saying A is bigger than equal than B, the max A B is A.
But what if A and B is the same?
It's the same, it still stands, yeah?
What?
It still stands, right? Okay, so if A is bigger or equal than B, if I put a sign, look, if I negate the sign, so minus A is smaller than minus B, okay? Yeah, because we change the sign, we have to change the sign, change from the bigger equal to less equal, right? And which one is smaller? This one, obviously, yeah? And then if we put the negative sign in the front, that will be A, yeah, which is exactly the same here. Yeah? Yeah? We just proved it. So the NegaMax, simplify it. So let's quickly write the NegaMax, and then we coming back to this alpha beta pruning, yeah? Because we talk about alpha beta pruning, but it's still we have to use the big if statement to distinguish between two scenarios. Yeah, two scenarios. Okay, I'm going to write the min-max first. NegaMax. Okay. NegaMax We have a state, we have a depth, we have what? Player. Or color, player, color, two player. One is red, the other one is blue. Maximizing, minimizing player, agent, opponent. If D is 0, yeah, if we reach the depth, yeah, or the state is the end state, is end, is the end state, is a leaf node of the game tree. What's end state? End state, what does it mean? What's end state?
End.
Yeah, end. In what kind of scenario? For the tic-tac-toe game, what's the end state?
3 in a row or the square is filled.
Where then? So someone has win, yeah, someone has won, or is a draw. So basically 3 kinds of scenario. Yeah, agent win, we give a positive infinity. Opponent win, we give a negative infinity. Or nobody wins, we give a 0. Yeah, so we return. In this case, we return a score evaluation of heuristic score of the state. So let's say score state. Now we're trying to, because this is NegaMax, so we can combine both scenarios into one. We set the initial score to negative infinity, and we're trying to maximize in both cases. For action, in action. Okay, so for kid in the state, okay, so this is the action would be the actions of the state. Yeah, what's the next move possible? And then the new state would be the successor of the current state. This is return a new state with the current action, and then score equals maximum of score. Okay, so this is the magic. Yeah, we talk about that. Score equals magic, and we are trying to go to the next round. So which I need to put the negative sign. Yeah, NegaMax. This is where the NegaMax. What's NegaMax? What's the nega? Yeah, put a negative sign. And a new state. Yeah, we pass in the new state. And the depth will be -1. Yeah, if we initially give a D depth, yeah, the maximum depth, we can search the tree. We set a hard limit. Okay, so this is the game tree. Yeah, this is the game tree. If we saying I'm setting the hard limit to step 3. So everything after, we just don't care for the moment because of the limited resources.
Once I gone on the computer to play Connect 4 with computer, and then when I was like just about nearly like to plan to win, and then the computers kicked me out of the game.
Well, why is that the computer kick you out of the game?
And then it just.
What's Connect 4?
It's like this square, and then you drop.
Can you draw? I don't know what you talk about.
Connect 4 is this circle. Well, I'm not sure.
You can use different color if you want. Okay, so these slots, yeah.
Yeah. Well, it's not exactly.
Oh yeah. Okay, and then.
Well, you drop these counters in, and it drops to the bottom, and then you can put some on top, and then you have to make 4 in a row.
So is it a 2-player game? You're playing against the computer? So you make one move, the computer make one move?
Yeah.
Okay, interesting. Maybe I can look.
It's like gravity, and you float.
I see, okay. So.
Down and
Okay, so the computer kick you out again? Why is that?
I don't know, it just...
Okay, but I guess that's a different reason, okay? Anyway. Okay, very interesting, I look it up. D-1, and then player. Player we need to neglect as a player as well, okay? Okay, so this is the NegaMax. So how about we introduce the alpha beta pruning? Yeah, let's review a little bit alpha beta, okay? Let's say this is 3, this is 5, and then if I have this 6 here, if we're trying to maximize here, yeah, and then here's something I don't care, something I don't care, something I don't care. Okay, I don't care here.
I don't care there.
So this is 3, 5, so I have 5 here. So we are minimizing here, right? We're minimizing here. Okay, so what's the value here?
5.
5. Why is that? Because this x is what? We are getting the maximum. So x, we found the first kid is 6. So what does it mean? This node is x is what? Bigger or equal than 6, right? Yeah? If x is bigger than or equal to 6, and we are getting the minimum in the experiment. What does it mean? Here, look. So this is bigger than 6, this is 5. So what? 5 is the winner. Right? Even we haven't explored this. Yeah? We haven't explored that, we don't care. This is uninteresting to us, right? Because it doesn't change the fact that x is bigger or equal than 6. Right? Look, yeah? So this is very useful. We just prune it. Okay? So in order to prune this as much as possible, we need to. Okay, so this is the thinking, right? A question. In order to have this kind of thing, we prefer to cut off this, yeah, as much as we can. So in order to do that, we need to search if we can sort these the kids of the same level. So do we need to sort the best, explore the best moves or the worst moves first?
5.
Yeah, I know. So in order to have this as cut off as much as possible, it's better we explore the trees with the moves, with the best moves first, right? Yeah, am I right? Does it make sense?
Yeah.
Yeah, because look, if I search this first, what happened? There is no cutoff, right? It matters the order of the kids. Look, I can search this node first, or I can search this node first, right? But if I search this node first, there will not be cut off. You can't prune it, right? Because you don't know, right? You don't know there's a 5. Does it make sense? 5 comparing to this node, this is better. So I have to arrange the nodes of the same level such that the best moves are explored first. Make sense? Yeah? Why is that? Because if I explore the best move, this is kind of better, yeah? Good move. Yeah? Yeah? If I explore this first, then I have more chance to cut it, right? We want that. Because of the higher chance to cut it means that
you can be lazy.
Yeah. You can be quicker. Yeah, exactly. Okay. So with this is the alpha beta pruning. So remember, we talk about alpha beta pruning and we can implement it using the min-max, yeah? But the problem is that you have to say if player is maximizing, then we do this bit of code, which is similar to minimizing, yeah? Look, this NegaMax. How is it compared to min-max? Come on, which one is better, min-max or NegaMax?
NegaMax.
Why is that?
It's because you can
Because what? Compared to this is the same as min-max, but it's the implementation is a lot simpler. Yeah, I don't have to check if, right?
And you don't have to write a lot.
Wait, no. Yeah, it's just that. Yeah. So first of all, I need to put to introduce alpha beta pruning. I have this alpha and beta. Yeah.
Pruning.
Yeah. Alpha beta. Alpha is basically the left boundary. Beta is the right boundary. Yeah. Yeah, everything else will be trimmed. You know the trim. Yeah, similar to the meaning of the pruning. Yeah, if it falls there, it's like a fence. Yeah, yeah. If it falls out of the left window, we cut it. Falls out the right window, we cut it. Yeah. Okay. So alpha beta. So this is the same. Yeah. So we have to put to give 2 parameters of that. Yeah. So first of all, I have to do this alpha will be equals max alpha score. Okay, we keep updating we keep pushing the left boundary. Okay, look, keep pushing the left boundary with this, and then if alpha is bigger than beta, then we just cut off break. We just terminate the loop. Okay, so now look, this is the same, but in order to go to the next one, we call it alpha beta here. We have to update the alpha beta boundary. So what values do I need to give to the next one, the new alpha beta value? Can you guess? Okay, so alpha beta. The next round will be what? Look, I put a negative sign here, so I put everything negative.
Negative A and negative A and negative.
If I put a sign, put a negative, so what happened to the?
Negative B, negative A.
Yeah, well done. This is not B, that's beta. It's a Greek letter.
Oh,
Greek letter, beta.
So is that
This
why?
is alpha.
So is it? So is but alpha for the A looks exactly the same.
Yeah, but it's a Greek letter. It's a very fat A. Right? It's I don't know. It's similar. It looks quite similar to A, but it's actually not. It's a Greek letter. Greek.
Oh,
You know Greek.
yeah.
Greek letter. Beta
So
alpha.
is that why the B is like on like looks like a tennis racket?
Yeah. Okay, so in this,
It's
yeah.
like one of the Chinese words, you know.
Obviously, we have to return the score as well. Okay. So here we have put the beta
it's a two
and then put
plus.
alpha. Yeah. Look, alpha, beta, and then we pass the minus beta will be the new alpha. Minus alpha will be the new beta. Okay. Yeah. Exactly. Yeah. Because look, if you put a sign. If we put a sign, alpha is smaller than equal to beta. If we put a sign, what happened? Put a sign, then minus alpha is bigger or equal than minus beta, right? So this is the lower boundary. Make sense?
Mhm.
This becomes the upper boundary. Yeah? Did you get it? Look, 1 is smaller than 100. Yeah?
Yeah.
So minus 1 is bigger or equal than minus 100. You see, when we put a negative sign, we have to change this. Yeah? Make sense?
Yeah.
Okay. So today we learn. Today we learned what? We just learned how to implement the alpha beta in the NegaMax, right? So in the NegaMax, and we also talk about the ordering of the moves, the action. So in here, action. So we have to to introduce. We can put a sorted, yeah. We can sort it this. Why is that? We can put the sorted moves from the good moves to the worst moves. I mentioned it just 5 minutes ago. Do you still remember? For the actions, yeah. Remember the trees. I want to explore the trees with the moves, good moves first.
Yeah.
So why is that?
It's because you can discard it later on.
Yeah, this is a very good move, right?
Mhm.
If this is a very good move, then there's a higher chance that I don't need to explore this. Yeah?
Mhm.
But if this is worst move, then I still need to explore it, right? Make sense? Yeah?
Yeah.
So the ordering of the moves help a lot in the alpha beta pruning. Okay, so we mentioned this. Okay, so today so last question, what have you learned today?
Oh, the beta NegaMax.
Alpha beta. This is the alpha beta on a NegaMax, right?
Yeah.
Yeah, we talked about alpha beta a few days ago, but we have to do you still remember the implementation? If maximizing, do this bit, yeah. Else do another bit, similar code, yeah.
And it's a bit long.
It's a bit long, yeah. The trick is what? We put the negative sign here. Yeah? Everything is trying to maximize. Look, the score is always negative infinity, which is the smallest number we can think of. And then, because when we change a player, the score needs to be negated, right? 100 score is good for me, it's bad for you, right? So when I pass the 100 score to the next round, in the perspective of you, it's like a minus 100. Am I right? Do you get this point? Opposite, yeah, because 100 is good for me, right? So when I pass the score to you, it's not 100 to you, it's minus 100 because it's good. Yeah.
It's bad.
Yeah. So this is where the negative comes from, and then we just keep passing the alpha beta boundary, and then in each round we keep updating the left boundary until it hits the right boundary, then we break. Okay, that'll be for today. Say bye bye to people.
Bye.
Bye bye.